Hello and welcome to the second part of Lesson 15. In this part of Lesson 15, we're going to examine the characterization of a solution of a biopolymer, kappa-iota carrageenan. Kappa-iota carrageenan is a sulfated polysaccharide derived from red edible seaweed, and it is widely used as a food additive. It's also been found to have antiviral properties and is hence used in nasal sprays to protect against various coronaviruses and against influenza. A spray application provides a good backdrop for this small case study. Let's suppose we wish to obtain the viscoelastic fingerprint of a kappa-iota carrageenan solution that works well in a nasal spray. Shear rheology, for example shear thinning, will be useful to understand the flow behaviour in the nozzle, and extensional rheology will be beneficial to understand the jetting processes involved in the spraying itself. We therefore might desire a constitutive equation that can describe both the shear and extensional properties, preferably using a single set of parameters. So let's dig into our arsenal of differential equations and see what constitutive model might help us the most. So let's motivate this again with some aims, think about the uses and think about the methods. So first of all, we might aim to quantify the nonlinear viscoelastic response of a solution of kappa-iota carrageenan in deionized water. We will also attempt to see if one constitutive equation can describe both the shear and the extensional behaviour of this particular biopolymer. In terms of uses, what we might want to do is to be able to come up with a fingerprint of this material. Now remember that biopolymers, in this case kappa-iota carrageenan, are a lot more variable in their molecular architecture potentially than synthetic polymers. So if we think about something grown in nature, how do we ensure batch to batch that we've got something that's actually going to work in the apparatus that we've designed? So we need to have a means of both fingerprinting and understanding how these different polymers behave. So in context of a nasal spray, we need to know something about the steady flow behaviour of these polymers, and we also need to know something about the extensional properties of these polymers, because if we think of the extension, it is that extensional behaviour that's going to cause the jets that have been sprayed to break up into droplets. So again, we can think of this in a quality control kind of environment. We might have multiple batches of kappa-iota carrageenan coming in from red seaweed, probably from red seaweed grown in conditions that are different in different parts of the world, and we want to make sure that we've got consistency such that we can roll out a product that we know that works. We'll probably have a specification of how much material we want to jet at any one dose, and we want to make sure that that is very well controlled. And so if the rheology of the material changes, the way in which the material jets will change, the way in which it will flow inside the nozzle will change, which means that we won't necessarily have the level of repeatability that we desire. However, getting a good rheological fingerprint of our material will give us great insight into whether or not a new batch of material is actually going to work in the intended manner or not. So, in terms of experimental methods, I'm again going to use parallel plate rheometry. Because it was convenient and because it was quick and because it was easy. I'm going to be using 25mm roughened plates, and that roughened part is quite smooth, is quite important because it prevents polymer slip on the plate. If you've got smooth plates that are effectively shiny that you can see your face in, if you're deforming a polymer, if it doesn't attach to the wall very well, the no slip boundary condition may well not apply. We've talked about this in previous parts of this course. If you roughen the plates, however, if you sandblast them, or you can even get roughness like serrations, then you've got a mechanical means of pinning that sample onto the plate. The rheometer that I'm using is not an Aries rheometer this time. It's an older machine. It's a controlled stress rheometer, and it's actually an old Bolin CVO120HR. For those of you who have been measuring the rheometric response of materials for quite some time, you've probably had one of these in your lab at some point. They were a very economical, cost-effective rheometer to use 10 or 20 years ago. The second rheometer I'm going to use is an extensional rheometer. What we need to look at the extensional properties of this material, and so capillary thinning experiments are a very good way of doing this. I'm going to use a TreeMaster Mac 2, which has two little pistons which pull apart from each other to form a fluids filament. The thinning processes are then captured by means of high-speed photography, high-speed video camera, and then subsequent image analysis allows us to look at the filament dimensions. So let's look at the first step, which is obtaining steady shear data. So I'm going to use roughened parallel plates, 25 millimeters in diameter, 1 millimeter plate gap with the solution of the biopolymer loaded between the plates. When I'm loading the solution between the plates, I've got to be very careful that there's no overspill around the plate edge, because what we're taking is a torque measurement from the plate. What we don't want is extra fluid surrounding or encapsulating the rim of these plates, adding to that torque response, because that will give us invalid data. So we've loaded the polymer, we've put the plates together to ensure good contact, we can see the fluid bulge out of the sides, then we've wiped off any excess very, very, very carefully, making sure we don't drag anything out of that gap, and then made sure that we've effectively got a clean system to go and do the experiments with. So let's jump to the data. There on the board I have put a plot of apparent viscosity as a function of shear rate. The shear rate on the x-axis is plotted logarithmically. The apparent viscosity, however, is not. And so we can see a region there at intermediate shear rate where the data looks a little bit odd. But if you look at the level of fluctuation in that data, it's not actually that much. If this was a logarithmic scale, we might get a little bit worried, but it's not. It's a linear scale. There's a little bit of noise there. Not too sure quite what's causing that. A few repeat experiments are in order just to see whether this is a repeatable effect or not. Almost certainly it won't be. But we just need to be aware that that is there. So there's something a little bit strange going on in these data, but generally speaking, what we have is a good data set up to around 500 reciprocal seconds. Now, compare this for a second against the steady shear data that we got in parallel plates for the polystyrene in the previous part of this lesson. We were unable to get good steady shear data for polystyrene in parallel plates above 1 or 2 reciprocal seconds, because the level of viscoelasticity was so much more that it was forcing the sample out of containment. For this system, effectively a dilute polymer solution, what we have is something with far less viscoelasticity and is something that is far better behaved, in a manner of speaking, in this parallel plate system. So we can get good rheometry data in steady shear up to relatively high shear rates. So we don't need to resort to capillary rheometry to get a complementary data set. So with these data, the next question we need to answer is, can we fit these data with the predictions from a constitutive equation? So we need a constitutive equation that can capture shear thinning and steady shear. So we're going to choose Giesekus. And I'll just put the equations that describe apparent viscosity as a function of shear rate for the Giesekus equation there on the board. If you remember back to previous lessons, we could see that there's a number of factors involved in this. The derivation is a complex one. And so the viscosity involves this parameter f, which is a lump parameter, which involves the lump parameter c, which involves that expression there. Now, if you look closely at the viscosity expression, you'll see that it's not quite identical to that we've used before when we looked at Giesekus. And that's because I've ignored the solvent contribution to the solution response. The solvent in this case is deionized water. It's a fairly low viscosity. I wanted to eliminate that because the capillary thinning expressions that I've got for the extensional rheometry don't include those contributions from solvent viscosity. And so if we can capture the steady shear data without having to include solvent viscosity, it just means that we can consistently use that same assumption across all the different experimental techniques. So I'm ignoring the solvent contribution. So let's see what kind of fit we get. There on the board, I've replotted the experimental data and overlaid the prediction of steady shear viscosity due to Giesekus. And we can see actually they fit pretty well. The way that I got these data, I just used Excel, You can use anything that you want. You can use any spreadsheet, or you can program a routine in any language that you want, MATLAB or Python or Octave or whatever. Sometimes you have to help the solvers a little bit. I used a nonlinear solver to find this using a least squares regression. What I tend to do when I'm fitting these data is give some reasonable guesses of eta 0 because we've got a low shear rate Newtonian plateau. So I set eta 0 initially to around 0.04 and looked at what results that gave me, and then chose an alpha and a lambda that got me somewhere in the right ballpark of the data, and then let the least squares solver do the rest. So we've got a set of parameters that can describe shear thinning in steady shear. Let's see if that same set of parameters can give us a fit to normal force data. So let's go and obtain some normal force data. So experimentally what I'm doing is I'm using steady rotational rheometry again. I'm using parallel plates, so I'm getting a combination of N1 and N2. I'm still using a 1 mm plate gap, and I'm still using roughened plates. So let's jump straight to the data. So there on the board I've plotted a normal stress difference. And what I'm plotting there is N1 minus N2, which is the data that you get if you analyse the normal force thrust, or the normal thrust that you get from a Bolin rheometer. So N1 minus N2 is what I'm plotting as a function of shear rate, and the green crosses there show the experimental data that I've obtained. And we can see again there's something a little bit strange going on around 100-200 reciprocal seconds. And almost certainly what's happening here is a little bit of slip. And so at these higher shear rates, the polymer's not quite attaching to the plates. It's slipped a bit, and so the force that we measure is a little bit less. Again, repeat experiments in this region would be very beneficial to help us get a better quality set of data. So, using the data that we've got, let's see how well the Giesekus equation can predict N1 minus N2 for us. So there on the board I've put the Giesekus expressions for N1 and N2. Note again these do not include the solvent contribution, and there on the board now I have put a plot of the experimental data and a plot of the theory. And what we can see is that over that range of N1 minus N2 before that slip event occurred, the Giesekus equation matches the experimental data very nicely, and that's using exactly the same set of parameters that I derived for the steady shear viscosity. So we have a unified set of parameters now that can both describe the steady shear viscosity as a function of shear rate and also the normal forces as a function of shear rate. So this is great, but this is all still in steady shear. Now, the question that we want to try and ask is, can these parameters also describe the filament thinning process? If we can get a unified set of parameters for all three deformation, that gives us a very strong basis to generate a good rheological fingerprint. So we need to obtain some filament thinning data. Again, what we're going to use is filament thinning rheometry using a TreeMaster Mark II. I'm going to jump straight to the results, and what I'm plotting here is the normalized filament diameter on the y-axis on a logarithmic scale, and that's d over d naught, as a function of time in milliseconds. And what we can see here is a really nice filament diameter decay as a function of time. If we look for a characteristic time scale, we can see that the filament breakup time, i.e. where the filament diameter will tend to basically zero, is going to be around 84.5 milliseconds. We can just see that intersection there on the x-axis. So we have some filament thinning data. We could do, again, some repeat experiments to reinforce the confidence that we have in these data and to get measures of error estimate, but I'm not talking about this here, although that is an important part of a characterization. What we want to try and ascertain, however, is do those parameters for the Giesekus equation that we've obtained in steady shear actually describe this curve as well? So what we need to do is to think about how we use the Giesekus equation to describe filament thinning data, and there on the board is an equation that we've seen before that gives us implicitly d over d naught if we explicitly state what t is. So rather than calculating d over d naught as a function of t, we're calculating t as a function of d over d naught. So we'll set a range of values for d over d naught. We're going to span 2 decades from 1 down to 0.01. And we'll see what time values that gives us, and then plot those time values out accordingly. The Giesekus parameters, the mobility parameter, the relaxation time, and the modulus are all the ones that I've already derived from steady shear experiments. And so there on the board is a prediction of the Giesekus model for filament thinning using the steady shear parameters. And what we can see, it's pretty close to the experimental data set that we've obtained. Now, given that we've only got one experimental data set here, and there does tend to be variation in these filament thinning experiments between data sets, we have probably got a very good description now of this filament thinning behaviour. It would be again enlightening to see 2 or 3 or 4 or 5 sets of filament thinning behaviour plotted out, and to see where that Giesekus prediction fits in amongst that family of data sets rather than just its one data set. Again, we need an idea of the experimental error here, and we haven't got that. If we look to the breakup time that's predicted using the model, we've got about 80.5 milliseconds, so 4 milliseconds shy of that one experimental data set that we've got. So let's just summarise what we've got here. There on the board, I've plotted the 3 sets of experimental data that we obtained. On the top left, we've got our steady shear viscosity as a function of shear rate with a Giesekus fit. In the middle, we have N1 minus N2 as a function of shear rate with a Giesekus fit, acknowledging that there was a slip event and that there will be a mismatch after that slip event. And there on the right-hand side of the board, I have a single set of filament thinning data, again with a Giesekus fit. And the parameters that we use in the Giesekus equation I've just put on the board as well, just for interest's sake. So what we've got here is one single mode, nonlinear viscoelastic model describing radically different types of deformation response. It is describing the steady shear response very nicely, and is also describing the extensional response very nicely. So if we wanted a fingerprint of a material that worked well, for example, in a nasal spray, we might resort to something like these data here that I've shown as those data that can guide us. So let's summarise a few key points. We've performed a slightly different viscoelastic characterisation this time. We performed fewer experiments and we used a differential nonlinear model. And we found that the Giesekus equation fitted very nicely both the steady shear viscosity data, the steady shear normal stress difference behaviour, and also the filament thinning behaviour. It has to be said, it's very unusual to be this lucky, to get one equation that will describe all these different deformations with a single set of parameters. If this happens, it's your lucky day. Go and buy a lottery ticket.